Hello, everyone, and welcome back to another University of Alberta Geotechnical Graduate Student Seminar. I hope everyone had a nice reading week and enjoy the warm weather outside. My name is Lan. As Kevin is still in another meeting, so I will get this seminar started. And no announcements this week, so let's just dive in. Today we are excited to bring you another presentation from Scott Martens, who is the manager of geotechnical engineering and geology at Albian oil sands mines by Canadian Natural Resources. Scott completed his undergraduate studies at UBC and subsequently completed his master's in geotechnical engineering here at the U of A. Scott has over 26 years of geotechnical engineering experience, with 15 years spent in the consulting industry and another 11 years in geotechnical mining operations. His professional focus has been on the design, construction, and safety assessments of tailings, hydroelectric and irrigation dams. He's also done work for the foundations for offshore oil and gas platforms and seismic hazard assessments for dams, nuclear power plants, and other critical infrastructure. The presentation today will speak on the geology of the Lower McMurray region and how they are heavily influenced by post-depositional processes, which greatly affects the design and performance of mining earth structures. Scott will provide examples of engineer properties with consideration given to site investigations, geotechnical designs, and geohazard risk management. Along with the presentation, if you have any questions, please type them in the chat box, and I will bring them up at the Q&A session after the presentation. So other than that, without further ado, please join me in welcoming Scott. Now, Scott, the floor is yours.
Thank you, Lang. So it's a great privilege to be talking with you. I always enjoy coming to the University of Alberta, virtually this time, I guess. I guess it's been more than 20 years since I did my master's degree at U of A. It feels like yesterday. But it's a very special place for me and a real privilege to be with you today. So I'm going to be talking about the engineering geology of the Fort McMurray area, focused on the design of mining earth structures. And the agenda here, we'll have a brief introduction. We'll talk a little bit about the context of tailings facilities in the oil sands. And then we'll go through the Fort McMurray geological setting, talk about the geologic units from youngest to oldest. And sprinkled in throughout that, there will be some engineering applications, as you see here. So the geology of any site significantly influences the design and performance of mining earth structures and civil infrastructure. And I call mining earth structures to be tailings dams, mine waste dumps, and pit walls. Infrastructure in a mining environment could be building foundations, tanks, roads, buried pipelines. So what do we want to get out of today? Some questions, I guess, for you to reflect on throughout the presentation. What influence does geology have on the design and performance of mining earth structures? What are some of the primary aspects of uncertainty in geotechnical performance that relate to the geology? How would an understanding of the geology influence site investigations? And what are some of the geohazards and measures we use to manage geohazard risks? Always like to start with a disclaimer. First of all, I'm not a geologist. I'm a professional geotechnical engineer, and I certainly have a working knowledge and understanding of geology. But for particularly complex issues, I always rely on the expertise of professional geologists and hydrogeologists on my team and from consultants. And secondly, I do often quote some material parameters that are typical of different geologic units in my presentations. Please don't use those directly in your own designs. As a professional engineer or geologist, you need to be undertaking a site investigation specific to your site and determining appropriate material parameters through field and laboratory testing. So why do we study geology as engineers? Well, first of all, it's cool. I think so anyways. I'm a bit of a geology geek, even though I'm not a geologist. But most importantly, it's to understand the geological risks and properly design mining structures so that they perform as required. Now, for an engineer, the purpose of understanding the geology is to make good engineering decisions. We aren't studying geology for academic purposes. We study geology because it influences our decisions. So the study of the site geology should always be linked to a specific engineering requirement like stability, seepage, or settlement. Now, there are two main types of tailings dams in oil sands mining. There's external tailings facilities. Those are constructed on the native ground surface outside of the pit area. And they usually provide 6 to 15 years of mine production as storage for tailings. They're often in the range of 40 to 80 meters high. And then we have in-pit dikes, which are constructed on the base of the mined out pit so that mining can continue on one side while tailings are deposited on the other side. And the mine pit ends up looking kind of like an egg carton where you've got these little containers, you've got tailings in some of them and mining proceeding in other ones. And these in-pit dikes are typically 60 to 100 meters high. So the geology, of course, is going to be influencing the design and performance of both of those. Now, outside of the mining industry, if you are building a hydroelectric dam, foundation conditions certainly influence the selection of the dam site. For mine tailings dams, there's often little ability to select the site based on favorable foundation conditions. And in the oil sands, the ETFs, external tailings facilities, are situated on the area of the lease that sterilize the least amount of the oil reserve because the reserves are valuable. We want to extract as much of the reserves as possible. And so we'll put the tailings dam, and since you can't, of course, mine underneath the tailings dam, we put the tailings dams in the area that have the lowest oil reserves. And that's typically in the areas with the thicker overburden, and that can include some challenging materials like the Clearwater Formation and deep Pleistocene sand channels. And we'll talk about those in detail. So here's an overview of the McMurray region geology, working our way from, let me find a pointer here. Working our way from youngest down to oldest. So at the ground surface, we have Holocene age materials, muskeg and lacustrine clays. So those were deposited in about the last 11,000 years. Underlying that are Pleistocene age materials, glacial lacustrine clays, outwash sands and gravels, and tills. And then there was an unconformity. So that was a period of erosion and a significant gap in age between 2.6 million years and about 100 million years. And during that period, there was over 1 kilometer of sediment that was deposited and deposited and eroded from the underlying materials. And that erosion substantially influences the behavior of those materials. So below the unconformity, we have Cretaceous age Clearwater Formation, offshore marine shales, McMurray Formation shales, that's the ore body. And then there's another unconformity. There's a long time gap between the McMurray Formation in the 100 million year range to the Devonian age carbonates and evaporites, which are in the middle 300 million year old age range. There we have a succession of limestones, argillaceous limestones, mudstones, anhydrites, dolomites, halites, gypsum, basically a lot of rock that can be dissolved. Underneath that, we have some sandstone and then yet another unconformity before we get to the Precambrian basement. That's more than 500 million years old. It's granites and gneisses. In the McMurray region, that's at about elevation 0. The ground surface, at least in the mining lease that I work at, is at roughly elevation 300 or plus or minus a few meters. So it's about 300 meters down to get to the basement rock. This is an overview here of the topography and the physiography of the oil sands mining region. You can see the Athabasca River, the Clearwater River and Athabasca River Valley. The dark black outline is the oil sands mining region, and the Athabasca River has significantly eroded into the bedrock here. The oil sands are much more widespread than this region here, but the mining region is concentrated along the Athabasca River Valley, where the overlying materials have been sufficiently eroded away that the overburden over the ore is relatively thin. So this is a typical geological cross-section within the mineable oil sands area. It's roughly an east to west cross-section. And what's notable here is that the younger strata, the Cretaceous age strata, are generally fairly horizontal lying. And the older materials, the Precambrian basement and the Devonian age rocks, are tilted down, dipping down to the west. This is a result of the formation of the Canadian Cordillera in the middle Jurassic to middle Cretaceous. So that's like starting at about 165 million years ago. And the weight of the mountain formation caused the crust to downwarp to the west. And that has a lot of influence on particularly the regional groundwater flow. And in this instance, you have precipitation that falls to the east of the mining region, and it flows down dip along those rock layers. And one of the regional groundwater discharges typically in the Athabasca River Valley here. But you've got this flow that's coming this way. And I mentioned earlier some of the soluble rocks, particularly halites, anhydrites, dolomites, gypsum, that are sitting in the Devonian age here. And some of the more soluble ones, like the halites, have dissolved progressively from the east working to the west and caused collapse of overlying materials. And we'll talk about that in more detail to come. On the next slide here is just a zoom in of what's in that little red box there. So this is looking at, focused on the Cretaceous age materials. We have the Clearwater Formation, Upper McMurray, that's a marine sand. And then we have the Middle McMurray, which is estuarine, tidal flat, highly channelized, and is usually the bulk of the ore body. The Lower McMurray is fluvial deposits sitting on top of the unconformity on the limestone, the Devonian age limestone. This is a photograph of one of the oil sand mine pits here. You can see it's a beautiful sequence of all the materials starting from Pleistocene age glacial tills through the marine Clearwater Formation, clay shales, and then the McMurray Formation ore body. Now, each of those mine pit benches is about 15 meters high, so that overall mine pit that you're looking at there is about 100 meters deep. So now we'll start our examination of the materials from the youngest down to the oldest. At the top, we have muskeg, an organic soil formed from decaying plants and trees. Muskeg can be actually quite strong if it's fibrous. Friction angles can be in excess of 45 degrees. On the other hand, if it's amorphous or more decomposed, it can have extremely low undrained shear strengths. And in both cases, it's very, very deformable. So if you're building a structure on top of it, you can expect very large settlements. For a typical, typical settlements in the fibrous muskeg can be 60 to 80% of the original thickness. So if you had a 2 meter thick layer of muskeg, you're going to anticipate 1.2 to 1.6 meters of settlement. And that's a lot of water, first of all, that has to flow away out of the foundation of your structure to like a perimeter drainage ditch. It also means a lot of settlement that can affect, if you have internal drain pipes, they might start flowing the wrong direction. It wreaks havoc on inclinometers because of all of that compression and down drag. It usually shears them off. You can spend a lot of money replacing inclinometers that you've put in through dams that are sitting on muskeg. And the permeability of the muskeg varies several orders of magnitude, starting from very permeable initially and becoming very impermeable as it compresses. And that's a photograph of some coarse woody muskeg that was, it's a test pit that's about 2.5 meters deep. Underlying the muskeg, we often have Holocene and Pleistocene lacustrine clays. These were deposited, sorry to back up. During the end of the last glaciation, around 11,000 years ago, as the ice margin was retreating northward, a large lake, Glacial Lake McMurray, formed at the front of the glacier, particularly due to the weight of the glaciers causing isostatic depression of the crust. Water was flowing northward in the rivers, forming a large delta on the southern margin of the lake. And so you had deep water glacial lacustrine sediments being deposited in the lake, and delta sands and gravels at the south end as the delta advanced into the lake. So these are some photos of the Pleistocene lacustrine clay. It's often pinkish in color. That can be diagnostic. It's often fairly low undrained shear strength and quite compressible. So some of the design considerations for the Holocene and Pleistocene lacustrine clays. Undrained shear strengths are what you would expect for a normally consolidated clay, typically an undrained strength ratio in the range of 0.22 to 0.27 or so. Bob Cameron in his 2013 lectures quoted typical strengths of 65 to 75 kPa, so it's lightly over consolidated. It's probably strain weakening, so if you start shearing it underneath in the foundation of your dam or mine waste dump, you'll get a peak strength and then a post peak and finally a residual strength. So you need to understand the pre-consolidation pressure, the maximum load your structure is going to put on it, and the rate of loading, and probably characterize the strength using a Shansep approach. It can, like the muskeg, can also have large settlements that affect the infrastructure. So for foundation preparation, we often remove those materials if they're critical to the stability of the structure, or you have to design for the strength and the significant settlements that will occur. Next, we have Pleistocene and Holocene fluvial sands and gravels. Those can be deposited in different environments. We have infilled, deeply buried channels that are incised into the McMurray Formation. There's large outwash plains of glacial fluvial sands and gravels. And there's paleo flood debris from the rapid outflow from glacial Lake Agassiz. These materials need to be checked for liquefaction susceptibility. They're often dense, but not necessarily so. They have fairly high permeability, and so they provide potential seepage pathways for process-affected water. Sometimes they're overlain discontinuously by tills or lacustrine clays. And so if they form aquifers that are surcharged by the elevated water table in a tailings impoundment, you can get artesian pressures near the toe that can influence stability, and they can contain rafts of other materials, and we'll see some of that to come. These are some photographs of the Pleistocene fluvial sands. They're often mined because they're excellent drainage materials for dam construction. You can see it's a nice medium grain sand in the photo on the left. In the photo on the right, you can see inclusions or small rafts of bituminous McMurray formation there. So it often, the PFS, the Pleistocene fluvial sand, often has materials that have been picked up, eroded away, and then deposited somewhere else. This is a photograph of outwash sand and gravel sitting on top of a Clearwater-derived till. And I mentioned buried channels and valleys. There's a number of major buried channel systems in the McMurray area that are eroded into surrounding soil and rock. The buried channels are inferred to have been eroded by glacial meltwater flowing underneath the bottom of the ice sheets under a lot of hydraulic pressure. They can be narrow and deep, and they often lie between your exploration boreholes. If your boreholes are a large distance apart, you can find a sand channel that's sort of sneaky hiding right in between your holes, and you don't even know it's there. They can be a complex series of stacked and superposed channels, segments, and deposits of different gradations, going from sand all the way through some clay beds and gravels and even meter-sized boulders. This is the bedrock topography of the McMurray region, and you can see again the surface mining area with a dark black outline, and these purple lines here are all of the system of buried channels that have been mapped in the region. This is what the buried channels look like in an exposure, in an excavation. You can see how there's complex interbedded, cross-bedded sands and gravels, some sorry, my voice is going a bit here. Finer grain materials injected into sands and gravels, so a very complex arrangement of materials. This is I had mentioned rafts before. This is a borrow pit into the. We've got Pleistocene lacustrine clays near the top. These are some glacial tills that are derived from the Clearwater Formation. We've got some Pleistocene outwash sands in the middle. And here you've got a raft of of reworked Clearwater Formation clay shale. And it can be very challenging if you hit something like this in a borehole to understand, well, what is the influence of that on the design of my structure? How are you going to incorporate those discontinuous features in the design? It's very helpful to, if you can ever see these things in an exposure like the mine pit wall or a borrow pit like this, to get a sense of the scale. Is a raft like this, is it the size of a piano or is it the size of an aircraft carrier? That will have a profound influence on your design. So some of the engineering implications to buried channels, they can act as subsurface conduits for process-affected water, tailings water from your impoundments, connecting surface water bodies or near surface groundwater with deeper or more extensive aquifers. Some of the control measures we take include cutoff walls, pumping wells, ditches that are incised into low permeability soil or rock to capture any groundwater flow, and liners, either natural or constructed at the base of the facilities. This is just an example of equipment used to construct soil-bentonite slurry cutoff walls through some of those sandy channels to prevent processed water from migrating off lease. Now, again, understanding the depositional environment for these buried channels and outwash plains is very important. You can see two conceptual interpretations of a buried channel here. On the left, most of the individual permeable units are isolated. And if you happen to get process affected water, if you had a tailings deposit sitting on top of here, and you got process affected water into a shallow channel, well, that would be easy to cut off with a cutoff wall or take care of with a pumping well or something. But if the interpretation is different, if those units are all connected, as is shown over here, then process affected water that gets into that upper recent fluvial channel could work its way all the way down into a lower aquifer. Geophysical techniques can be very useful to identify some of these channels that might be sitting in between your boreholes. Electrical resistivity tomography, that's what's used for this cross-section here, is a very useful technique. But you do need to understand that all geophysical techniques depend on a strong contrast in the properties that are being measured. And so if you don't have such a strong contrast, resistivity in this case, then you can spend a lot of money and not necessarily get any useful results. So some things to reflect related to seepage control. We are, of course, required to prevent deleterious impacts from groundwater flow on other surface or groundwater bodies. So you need to think about how does the geology influence the design and the operational controls to prevent seepage of process-affected water. And how would your knowledge of the geology, like we just discussed, influence your site investigation plan? So here's a schematic cross-section here, and showing we have several, perhaps an outwash sandy plain here, buried in some till, another till layer, a deep channel incision of Pleistocene fluvial materials, some Holocene deposits, and our oil sand body. And if you were going to put, say, a tailings dam sitting up here, where's the potential seepage pathways? You know, could the seepage get around that till, which is discontinuous, and then actually discharge on the hillside? If you were going to build a side hill tailings impoundment over here, there's the potential for seepage to work its way into that outwash sand. And so you might need to line the side of the impoundment there to prevent that. If you are doing in-pit tailings storage, you might actually, if you're going after the oil sand over here and that was the edge of your pit wall, that might intersect that lower buried channel, and that could again provide a channel for process-affected water seepage. And so you would need to prevent that either by a cutoff wall, pumping that channel down. There's different ways of addressing that, but you need to understand the geology to make sure that your mitigation is suitable. So now we'll move on to the Clearwater Formation clay shales. The Clearwater Formation is a transgressive marine sediment deposited in an invading sea. And so for the entire Cretaceous age deposits that we're going to be talking about here, the Clearwater and the McMurray, they were all deposited in a transgressive marine environment. So the bottom, we'll flip our ourselves around for a minute and talk from the bottom up. The lowest or earliest units of the McMurray Formation were an onshore deposit. And if you were standing in the same location for several million years, initially the ocean would be a long way away, many kilometers away. And over time, the ocean got closer and closer. It eventually would have drowned out the location you were standing, and then that would have become a deep water location. So the Clearwater was deposited, it's the youngest of the Cretaceous, and it was deposited in a deep water marine environment. The full sequence is about 70 meters thick, though it's eroded near the Athabasca River Valley. It's got a lot of high montmorillonite clays. Liquid limits can be as high as, that I've seen, about 210 or so. It can have some very weak zones in it that are laterally continuous for large distances. That can be very difficult to identify in the core. And low shear strengths as low as about 7 degrees have been mobilized in the field. The lab strengths, because it's a marine deposit, and so the pore fluid chemistry is actually saline. If you do your testing in a distilled water bath for, say, a direct shear test, you're actually replacing the saline pore fluid with distilled water, and that can influence the strength results. We have rafts of clear water, like I showed you in that one photograph, that are glacially transported, and they can have a wide range of strengths. And the pore pressure response of this material is very challenging. The stress-induced pore water pressures can be very high, with B bars, if you're familiar with that term, being in the range of 0.7 to 1. So that's the ratio of the change in pore water pressure to the change in vertical effective stress, or vertical total stress, sorry. And because the permeability is so low, 10 to the minus 12 or so, it can take many decades for those excess pore water pressures to dissipate. These are some examples of clear water cores, core tubes on the left that have been cut in half so that you can see the interior of the core tube, and some samples where the core has been pulled apart on the right. When you're just looking at the core tubes like that, it can actually be extremely difficult to find the weakest layers in the core. They're not visually obvious. And one of the challenges that we have, sometimes people will take an Atterberg limit test, every couple meters, and to get an understanding of the liquid limits and the plasticity of the clear water, and potentially how weak it is. The challenge there is that the weakest layers are typically only a couple of centimeters thick. And so if you had a 2 centimeter thick weak layer and you did a liquid limit Atterberg limits every 2 meters down your core, you'd only have a 1% chance of finding the weakest material there. So it's helpful to break the core apart and examine it for shear features like is shown on the right. And a strategy that I use is to do very, very detailed water content sampling every couple of centimeters, combined with downhole geophysics, natural gamma and density logs, and using some techniques that are described in the paper there. And there's a full reference section at the end of this presentation. You can look these up and use that as a strategy to try and find the weakest layers in the clear water. And I'll just skip through that in the interest of time, but there's more detail in that paper. Looking at the Atterberg limits of the clear water, you can see they plot very close to the U line there. Again, that's a suspicious indicator that the dominant clay mineralogy is montmorillonite. And you can see here we've done some X-ray diffraction and correlated that with the liquid limit. And you can see that there's a strong correlation between percent of montmorillonite as clay minerals as compared to the liquid limit, which can go as high as just over 200. So the next Cretaceous age unit is the McMurray Formation. This is the ore body, and as I noted, it was also deposited during transgressive sea conditions. It's divided into 3 members, the upper, middle, and lower McMurray. The gradation varies all the way from medium sand to a clay. So here's a depositional cross-section of the McMurray Formation. You can see the oldest deposits were onshore, like I said, and as you get younger, you get to shoreline, estuarine channel, tidal channel deposits, and nearshore marine as the youngest deposits there. The lowest Lower McMurray is deposited on top of the Devonian Paleotopography, and it's a channelized onshore environment. This is a schematic of the depositional setting of the Lower McMurray. So this is, again, that onshore deposit. You can see how it's a very complex arrangement of a braided fluvial system with sand channels offshore, overbank muds, point bars, and some coal swamps. And it's often very helpful to see these units in the exposure of a pit wall. If you ever have the opportunity to see them in the pit face, it gives you a lot of insights that you don't just get from a drill hole log. So here's an illustration of the complexity. This is the Lower and Middle McMurray formations. And you can see if you drilled a borehole there, and maybe you drilled another one over there, you would think, well, that's a pretty simple, straightforward layer cake geology there. But without understanding the overall depositional environment, you might not realize that lurking not very far away at all, the geology is completely different. You can see one of those channels that's been incised into the earlier materials and deposited a number of clays that weren't present in the location of your boreholes over there. Now, I often find it extremely helpful to look at modern analogs of the depositional environment that we're working with. That gives you a sense of the depositional processes and the scale of the features. So these are two good modern analogs of the McMurray Formation. This is particularly the Lower McMurray and the Middle McMurray, which are the onshore and tidal estuarine depositional environments. So we have the Parana River in Argentina on the left and the Mackenzie Delta in the Northwest Territories. And you can see I put a little indication for scale here. You can see that there's a little lake that's got a scale of about 1 kilometer. You can see that the river channels are much narrower than that, maybe a scale of about 100 meters or so. And that gives you a sense of if you're planning a site investigation, well, how far apart should you put your boreholes so that you don't miss one of those features? And the other thing to consider is if you were building a dam that was aligned in that direction, you can see in this case, the dark gray layers are clay deposits in abandoned oxbow channels. And if your dam was oriented that way, well, what would be the influence of the orientation of those clay and sand deposits? And how would that differ if your dam was oriented in that direction? So now the Clearwater and McMurray formations and the underlying limestones are significantly influenced by a number of post-depositional processes. That can include differential compaction, mud beds settling more than adjacent sandy channel infills, erosion causing vertical rebound and high horizontal stresses, underlying salt solution, dissolution of all of those soluble units like the halites that we talked about and we'll come to in more detail. The effects of being glacial overridden, glacial drag and loading and unloading, horizontal stress relief from that can cause, like from the erosion of the Athabasca River Valley causing valley rebound. And then you also have the subglacial tunnel valleys. And the timing of all of these post-depositional processes, a lot of them occurred immediately or shortly after the time of deposition, but some of them are ongoing to the present time. This is a photograph in the mine pit of faulting in the Lower McMurray. You can see the fault there. That's not a fault from an earthquake. That's due to the dissolution of the underlying halite formations. This is some downwarp beds in the. This is in the Middle McMurray. You can see how the bedding warps down like this. So that's a collapse feature. And again, due to differential solution of the salt or halite that was in the deeper Devonian age rock is caused that down warping. And all of those clay beds now are going to be extensively sheared because of the way that they've collapsed into that hole. This is some core photographs of Middle McMurray and Lower McMurray cores, middle on the left, lower on the right. And one of the challenges that we have is we install piezometers, in the rock to measure the pore water pressure, maybe for understand the pit wall stability? Well, if you were putting a piezometer into this material and look at how finely interbedded the sands and the clays are, what would that piezometer actually be measuring? And is it actually giving you an accurate indication of the pore water pressure? Also looking at how finely interbedded that is, how would you identify what is the potential sliding layer? If that borehole was drilled near the pit wall, what units there are going to influence the stability of your pit wall? You can see it's exceedingly complex. This is a core that we took a long time ago, and it shows how the influence of very small features can have on the stability of a structure. This is a 5 centimeter thick layer of high plastic clay that we subsequently caused a shear zone underneath the dam. And it was situated in the middle of a 10-meter thick sand layer. A number of complications there. First of all, would someone have even necessarily paid attention to 5 centimeters of clay sitting inside of 10 centimeters of sand? And secondly, if you even knew it was there, how would you measure the pore water pressure in that clay? It's not possible to install a piezometer in a layer that thick. So how do you really know what's going on in there? This is another photograph of faulting in the McMurray Formation. You can see a series of down-drop blocks there. And again, if that was your pit wall that you were analyzing the stability for, what would a piezometer completed somewhere in there, what would that be telling you? This is some Lower McMurray floodplain overbank facies here and back swamp facies. The back swamp is one of the weaker units, and so when it's fairly high plastic, and so when there's deformation, like due to underlying collapse, then the strains concentrate here and heavily shear this material. You can see how sheared and flaky that material is there. These are some blocks that I pulled out of some test pits in the back swamp. You can see how planar and there's obviously been a lot of shearing on that sample there. It's heavily slick and sided. Some Atterberg limits from the Lower McMurray. Not as high plastic as the Clearwater Formation that we looked at earlier. It actually spans the full range from low plastic, medium to high plastic, with highest liquid limits in this case being around 80. So not super high, but certainly high enough to be problematic. So some of the design considerations for pit walls in the McMurray Formation. It's very heavily over consolidated. Remember, we talked about that more than 1 kilometer of erosion from over top of the McMurray Formation. That means we've got very high locked in horizontal stresses, high K-naughts, and a lot of horizontal rebound when we're mining the pit walls. It's gassy. There's a lot of, there's methane that's dissolved into the bitumen that comes out of solution when the total stress is reduced. And that tends to maintain a low state of effective stress when you're mining through it. And there's varying dip angles based on both the mode of deposition and the post-depositional processes that can affect the pit wall stability. Now, one very useful tool for understanding the dips of these units here is called the dip meter. The dip meter here is a micro-resistivity tool that takes measurements of the resistance around the circumference of the borehole and can be used to identify dipping layers. And a dip meter plot is we call them tadpole diagrams like this. The x-axis here is the dip angle, and the direction of the little tails of the tadpole is the dip direction. So for example, over here, we've got a dip of about 10 degrees to the north. And over here, you would see a dip of about 18 degrees to the northeast, or here 5 degrees to the southwest. And that can be used in the design of the pit wall to understand if the dips are unfavorably dipping out of the slope. So some of the pit wall failure modes and the geologic influences. Over here, high stress relief due to that high locked-in horizontal stresses can cause slabbing failures. If you have adversely dipping clay beds, you can have shallow block slides. Gas exsolution from high-grade bitumen can cause slumping and bulging. And and low shear strength from underlying weak clays like those back swamps that we saw a couple slides ago, or like the Paleosol on the top of the Devonian can cause large slumps due to basal shearing. We talked about the challenges of understanding what the water pressures are. If you're tasked with doing a slope stability analysis of the pit wall, you need to put a water table into your analysis. And we saw how variable the geology is, how interbedded it is. And so you have to make some assumptions for the water table, but you really have to ask yourself the question, how accurate is that water table? In reality, there's probably multiple stacked perched water tables that are occurring in the pit walls. And how are you going to represent that in your slope stability analysis? This is a photograph of a large multi-bench failure that occurred a number of years ago at one of the mines. It was the result of an interaction between rich ore flow. We saw that from gas exsolution a couple slides ago. Rich ore flow on the bottom bench, weak dipping shales above that, and some water infiltration from rainfall onto the benches that all work together to cause a large instability. This is some instability on some upper benches here. This is slumping of the overburden above the ore body in weak Clearwater shales and Clearwater-derived tills. This photo shows rich ore flow, gas exsolution, and here you've got some very steeply dipping clay beds that are causing slumping into the pit. So some of the design considerations for the McMurray Formation: in the upper McMurray, there's thin layers of weak shales, that even a very thin layer, like 10 millimeters thick, clays have been mapped to be continuous over hundreds of meters. The middle McMurray Formation can be highly channelized with adverse dipping clays. The lower McMurray can have weak, high plastic, sheared clay shales. The sandy layers, the bituminous sands, are actually, like the oil sand, is actually very dense and strong. Friction angles can be in the range of 60 to 70 degrees. That's due to the heavily over-consolidated interlocked particles, a locked sand. It's not the bitumen that contributes to that level of shear strength, and the excellent papers in the 1970s by Dussault and Morgenstern explain that all. So now, how does, in application to your geotechnical instrumentation, how does knowledge of the foundation geology influence your instrumentation and monitoring program? And how does it influence your confidence in your understanding of the system based on the instrumentation data? Questions to ponder. Now we'll move on to the Devonian. The uppermost Devonian surface, this is on top of the limestone, is sometimes a paleosol. So that's a rock that's been weathered to a soil with a high clay content. It's typically greenish gray, though we found some interesting colors due to chemical weathering. And you can see here this weak clay paleosol has formed a shear surface that's polished, shiny, and smooth, and is just waiting to be another shear surface if you build a dam on top of it. Here you have an exposure of Devonian Paleosol in its more diagnostic, typical greenish gray color. Some exposure, a test trench that was excavated into the shaly limestone. So this is below the Paleosol now, to assess the continuity of weak layers for the foundation of a dam. And here we're mapping, this is a photo of the side of the test trench, mapping the dip angle and continuity of major joints and shear zones. So in the Devonian carbonates, some design considerations: there's an extreme strength range all the way from the Paleosol, which can be, sort of a shear strength in the range of 9 degrees, up to some very, very hard limestones that can have unconfined compressive strengths of many tens or hundreds of MPa. So you need to understand the discontinuities, the spacing of the discontinuities, the existence of pre-existing shear zones that might be there, and particular whether or not the Paleosol is present or absent. I'm just going to skip that because we're running a little low here on time. We'll talk a little bit about geohazards now. We've been mentioning this on and off throughout the presentation, that in the lower Devonian sequence, there were a number of very soluble rock types, particularly halite. which is table salt. And they're represented in this uppermost sketch here as the pink layers. Over time, starting in the pre-Cretaceous, there was dissolution of those units. Again, remember the groundwater flow was down dipped from the east towards the west, and so the dissolution front moved from east to west, and the overlying materials collapsed, creating a complex sequence of faults. And the Lower McMurray was typically deposited in topographic lows on that collapsed surface there. The collapse was made a little bit more complex by the presence of some discontinuous reefs. Those soluble rocks were deposited on-lapping onto the reefs, and then when the soluble rocks later dissolved, you got discontinuous levels of collapse where the reefs didn't collapse. They were insoluble, but the materials in between them did, and you can see the collapse patterns in that schematic there. So there have been up to at least 90 meters and up to even 200 meters of removal of the prairie evaporite soluble rocks. So you can imagine that it's kind of like longwall coal mining, where you've got this mining front, or dissolution front in this case, progressing to the west, and then as the rocks dissolve, the ground progressively collapses behind it. That's led to some large-scale faults, but also a series of small-scale sinkholes and breccia pipes due to dissolution of gypsum. And you know, it's nice to be able to know where these features are so that you can account for them in design. Unfortunately, most geophysical methods don't have the resolution to image these small-scale features that could, for example, allow groundwater flow from a lower aquifer up into the mine pit. One method that has been used successfully is pumping tests with a network of observation wells to see if there's hydraulic connectivity across the formations. These are an air photo on the top showing some suspicious circular lakes. If you're working in the Fort McMurray region, you should always be very, very suspicious of any lake that is a nice circle, and in particular doesn't have a inflow or outflow stream. The lower cross section there in a mine pit shows two very distinctive collapse features here, where the ground has collapsed from the bottom, or the sinkhole is propagated from the bottom up, and then the overlying materials have collapsed down into it. Here's another sinkhole, like I mentioned, a suspicious circular lake. This was about 20 or 25 meters across. It just looked like a little lake sitting there. When the water was pumped down out of it, you could see there were vertical walls on that sinkhole. And the evolution of that sinkhole, it was called hypogenic karst. The dissolution starts at the bottom and works its way upward. So it could actually be hiding just below the ground surface there and pose a potential hazard, not only for groundwater flow, but for the safety of workers. So some of the risks related to geohazards: water ingress into mining areas as you're mining through the pit. It could cause deformation of dams or other structures that might be constructed over faults or sinkholes, and ground collapse that could affect worker safety. We assess the risks by looking for areas of steep dips on the Devonian surface, collapse features as we're mining through the overlying strata, like we've seen in some of those exposures on the pit walls, and in terms of the potential for inflow into the mine pit, we're wary of areas with large hydraulic head differences between the Devonian aquifer and the pit floor. Some of the risk mitigation methods are to leave a cap of oil sand in place over areas of identified high risk, proactively depressurize the Devonian aquifer ahead of mining, and have a rapid response plan to construct containment around an inflow if there is water into the pit. And the very final topic we will cover here in just a couple of slides is on the seismicity of the Fort McMurray region. The basement rock, as I mentioned before, Precambrian granites and gneisses. The Fort McMurray is now situated on the Canadian craton. A craton is the ancient stable portion of the continental crust that survived all the merging and splitting of continents. The little image on the right-hand side there shows an interesting map of Pangaea with the modern political boundaries mapped on top of it. So Pangaea was the supercontinent that was assembled about 335 million years ago and began to break apart about 175 million years ago. And everywhere where it broke apart, there's rift zones where the crust is weakened, and those are areas where we tend to get more earthquakes. You can see that Fort McMurray is sitting in the middle of the Canadian Craton and is a long way away from any one of those rift zones. And so it's in a fairly an extremely low seismicity region relative to other areas of the world. So typically seismic hazards do not govern the design of tailings dams in the Fort McMurray region. And this slide here just shows, again, Fort McMurray plotted on a map of all the earthquakes that have been recorded in Canada. And you can see that the central zone, the Canadian Craton, is highly aseismic compared to the subduction fault zone on the west coast of British Columbia, or some of the interior rift zones in southern Ontario and Quebec. So that is the end of the presentation there. I've got 3 slides worth of references. I will provide those to Lang or Kevin, and they can make them available to people if you want to look up. I think all of the illustrations that I have and used in the presentation are referenced over here, and you can look into more details. So thank you very much for your attendance, and I'm happy to take some questions now.
So thank you a lot, Scott, for the presentation. Quite a lot of information, and thank you for sharing the insights on the challenging geology in the Fort McMurray area. And so those, just note that this presentation will be uploaded in our YouTube channel. So if anyone is interested in looking back, you can just go to the channel to check it out. And the link is listed in the chat box. So now we're coming to the Q&A session. Now we have a few questions here. I will just read one by one. The first one is from Anna Madison. The question is, how do you manage the gas exhaustion of the rich feed during mining?
Yeah, that's a challenge. It's one of those things that's going to occur. It's often worst on south-facing slopes that get a lot of sun, that warm the oil or the ore body and the highly bituminous layers. One of the things to be careful of in those layers, which are getting a lot of gas exsolution, is to control the shovel mining so that they don't overmine, because you'll actually get the rich ore flowing towards the shovel, and the shovel can sometimes stay in one place and the ground comes to it. You have to have careful controls on that so they don't overdig it, because you'll end up with a wall just progressively collapsing above the rich ore. And so it's just really about strict controls and observations during the mining when they're working in those more challenging areas like that. And it's also taking that into account in your pit wall design, like that one illustration I had of that failure. In that case, there was some dipping clay beds in the units above the rich ore. And so by overmining the rich ore, there's the potential to cause shearing on those steeply dipping clay beds that will weaken those beds and cause collapse of those materials. It's sort of a chain reaction.
Thank you, Scott, for answering this question. Next one is from Dr. Nick Beer. The question is, are you reconciling your geological model from drilling logs with observations during mining and excavation operations?
Yes, we do. We take, particularly around areas of interest like the ultimate pit walls, we take a lot of photographs of the pit wall as they're mining through it, and we do reconcile the observations and try and improve the resolution of the overall model from the mining observations. The drilling program, like the ore delineation drilling, typically works in a sequence of about 400 meters spaced drill holes, more than 5 years out to define the reserve model. And then when we get to about 5 years, we drill at a 200-meter spacing. And by the time we're 1 year away from mining, we drill at a 100-meter spacing. But that's the closest spacing that the drilling is typically done, unless there's a specific need to go at a tighter spacing than that. And so you can see from the photos that yes, and a lot of things can happen in between boreholes that are 100 meters apart. And so we do reconcile that as we're obtaining information from the exposures.
Great. I also have a question. How would the dissolution of the underlying salt formation change the local stress in the upper structures in that region?
I just missed the word, change the
local stress in the upper structures in the region.
Yes. That's a good question. I think it just probably makes it more complicated. It probably relieves the stress in some cases to an extent because you have faulting and collapse downwards, but we do see still indications of fairly high horizontal stresses. People who have studied the K-Knot in the McMurray Formation, for example, have indicated that it's probably in the range of 2 to 5 K-Knot. So, well above 1. And that causes a lot of movement as you're mining through the ore bodies. And it can be very challenging. If you have inclinometers sitting just above the pit wall, you'll see a lot of movement on the clay layers. And what the engineer who's responsible for the stability of those pit walls has to make a determination. Is the movement that you're seeing, is that an incipient failure, or is it just elastic rebound due to the relaxation of those horizontal stresses? And when you're watching your inclinometer movement rate increase, it can be very challenging to make that determination. Is this just is it just regular rebound, not something to be concerned about, or is it something that's progressing towards a failure?
All right, thank you so much for answering this. Another one's from Osman. The question is, what is best practice to measure the pore pressure response of thin, weak clay zones, and how is it best factored into design considerations?
Yeah, I think, well, it's a whole nother topic, but our best practice for measuring the pore water pressure response in thin zones is to use a vibrating wire piezometer in quite a narrow sand pack, and then complete the borehole with a bentonite chip seal. We do not use a fully grouted piezometer for trying to measure the pore water pressure response in a low permeability layer like a clay layer. You will always underestimate the pore water pressure response. But if the clay layer gets too thin, if it's thinner than, probably 0.5 meter thick is the absolute minimum that you could reasonably accurately measure the pore water pressure response, more likely 1 meter or so to get a good seal of the piezometer in there. So I think the important thing is to know is that if the clay layer is thinner than that, you don't actually know what the pore water pressure response is, especially about the pore water pressure that's going to be generated due to shear. If the clay starts to shear, if it's a normally or lightly over consolidated clay that is contractive and generates excess pore water pressure during shearing. And so you need to take that into account during the design. Understand that there's uncertainty there. And if you do have pore water pressure measurements, don't believe them religiously as if they're the absolute truth. Understand that there's a significant level of uncertainty and factor that into your design.
All right, thank you. Another question coming up is from Colin Drager. What type of in situ testing is done to quantify K-Knot and the modulars to estimate deformations and delineate between plastic and elastic during mining?
Well, that sounds like a thesis right there. There have been pressure meter testing, like drilled pressure meters installed in boreholes to measure the horizontal stresses, and you can get an estimate of the elastic modulus there too. Another way of doing it is actually to back analyze some detailed measurements of the pit walls. You can get an indication of well, both the modulus of the unit and of the horizontal stress ratio from an analysis of the observed performance of the pit wall, though that's very difficult to do because there's so many variables. So the solution to that back analysis is going to be highly non-unique. You can match the deformations using a whole series of different combinations of parameters. So it's something that has not been extensively studied. There have been some tests done with pressure meter, but it's probably an issue or an area for some further research for sure.
Great, thank you, Scott, for answering these questions. And that's all I have here. And thank you again for making this presentation and spending time with us. It's right on 1 o'clock. So,
perfect.
Thank you everyone for joining this seminar. And we are looking forward to the next one in next week. Other than that, I hope you have a great day.
Thank you very much.
Thank you. Thank you, guys. See you next time. Bye-bye.